spoken on field theory and cosmology. Today I'm going to talk about black hole thermodynamics, especially about dynamical descriptions of Born infill at this black hole. So we begin with an introduction, giving a definition of black holes and the motivation behind studying these objects. Second, we introduce the thermodynamics of a black hole, and then we focus on the dynamical descriptions of Born infill at this black hole thermodynamics. And we finish with a conclusion. So, an asymptotically antidisciplinary black hole in 4 dimensions is a solution of Einstein equation. So this equation is derived from the principle of least action. We have R here is the convection tensor, G is the metric, and T is stress energy transfer. Lambda is the cosmological constant. So this cosmological constant characterizes the spacetime. When it's positive, the spacetime is called d theta, ds, and this corresponds to a spacetime in expansion, like our unit. And when it's negative, the spacetime is called anti-d theta, eds, and the universe in contraction or in shrink. Okay, so eds stands for anti-d theta. So in the vacuum, the metric of a static spherically symmetric black hole reads like this. So static doesn't depend on time. Spherically symmetric has the symmetry of a sphere. So we can see that the metric is characterized only by this function that we call it the metric function. So a black hole has a horizon. So at the horizon, the metric function vanishes. So we have RH is the horizon radius. So the question is, why are we interested in this objects or in ADS black holes or in ADS spacetimes generally? So there are several reasons, but particularly 2. The first one is string theory in quantum gravity. So the string theory is formulated in ADS spacetime. So to study black holes using string theory or testing string theory in black hole context, so we should do this in ADS spacetime. The second one, which is more important and more interesting, is the gauge gravity duality, that we call it usually ADS safety correspondence. Okay? This ADS safety correspondence states that the gravitational physics in the book of an ADS spacetime corresponds to a gauge theory on the boundary, particularly to a conformal field theory on the boundary. So, if we describe or if we study a black hole in a ADS spacetime of a dimension d, so we are indirectly studying the conformal field theory on d-1 spacetime. That's why we are interested in ADS spacetime. So, the black hole thermodynamics is studying black holes as a thermodynamic system, defining the mass as the enthalpy of the energy, and we can write down the first principle of thermodynamics, T is temperature, S is the entropy, and so on. So we can ask what's the temperature of a black hole and what's its entropy. So the correspondence is here. So the temperature of a black hole is its surface gravity. The entropy is the horizon area. The pressure is cosmological constant, and so on. So now we introduce the Born infill black hole. So a Born infill black hole is an electrically charged black hole, but we don't know linear electrodynamics. So here we have the Lagrange of Born infill. It's non-linear because of square root. F is the electromagnetic tensor that we find usually in electromagnetic interactions. B is a constant which is related to the string tension alpha. So where string tension alpha tends to 0, B tends to infinity, and we can develop this Lagrangian to find out the usual Lagrangian of electromagnetic interaction. So the von Ampere Lagrangian is a generalization of the usual electromagnetic interaction. So the metric function is given here. So it's a little bit complicated. It's not good. And once we have the metric function, so we can compute all thermodynamic variables. So we can compute the mass by setting Fr to 0 at the horizon. So we can compute the mass, the temperature, the quantity, the volume, and so on. And to study the stability of the black holes and the stability of each phase, we define the free energy as in the usual thermodynamics. And here we have the free energy or the on-shell free energy. So we can recognize three phases or three different phases. First one is the thermal radiations, that's me at the black holes. Second is small black holes because they are small. Large black holes because they are large. And here we have a triple point, that's me, the coexistence of three phases. Here we have a phase transition, a first phase transition between thermal radiation and large black holes, which is called Hawking-Page transition. So very famous transition because it corresponds on the gauge theory to the confinement of quarks. Here we have a first order phase transition between small and large black holes. At this point here, we have a second order phase transition. We can also here have a first transition from thermal radiation to small, and then from small to large. So in this talk, I will focus only on the triple point, which is here, and I have here the free energy, off-shell free energy, in a function of R. So we see that we have three minimum, which corresponds to three stable states that have the same energy. This energy is the same. Okay? So the black holes, we suppose that the black hole, for example, is here, so we can make a transition to small or to big. So studying this transition, that's what we call the dynamics of the dynamical descriptions of black hole thermodynamics. So to study this dynamics, we use the statistical physics tools. Here we have the Fokker-Planck equation. Rho is the density of probability, D is the diffusion coefficient, beta is the inverse of temperature, and G is free energy. So we solve numerically this equation, and we will have here the equation. So the stationary solution that we can see, we have three heaps. That means we have the coexistence of three states. Okay, thermal radiation with R equals 0. That's mean there's a black hole, small black holes, and large black holes. Here we have the probability of each state. That's mean the large, small black holes, and thermal radiation. So we have initially a black hole, a large black hole, and you see that the probability decreases in time, and you see that the thermal radiation and small black holes probability increase simultaneously, and we see here that in small black holes the probability becomes larger than the large one, and that's what we call the strong oscillations of black. Whereas here when the black hole is small, initially small, so we will have the increase in the probability of thermal radiations. That means that small black hole decays quickly to thermal radiations before to make a transition to large black holes. And to finish, here we have the distribution of the first passage time. That means the time or the necessary time to make a transition from one state to another. So here we have when the black hole is small, okay, to make a transition from small black holes to large black holes, and for small black holes to thermal radiation. And here in red is the transition from large black holes. So you can see that the large black holes has more stable than small black holes. The small black holes can make a transition to large black holes and also to thermal radiation. And that's what we see here. We have two distributions. The first one that describes the transition from small black holes to thermal radiation, and the second one describes the transition from small black holes to large black holes. So we can see that small black holes decay quickly to thermal radiation because they are unstable. And here we compare between small black holes and large black holes. This means the transition from small black hole to large and to large, from small black holes to large black holes and from large black holes to small black holes. So we can see that we have the same time here. That means they are symmetric because they are the same potential barrier between them. And we finish with our conclusion by lecture. Okay. Thank you.
Is there any question? So,
I'm not familiar with this field. When you describe the probabilistic evolution of black hole, you said you use the Fock-Planck equation. Why use the Fock-Planck equation? How about the diffusion equation? Is there a reason why you choose the Fock-Planck equation?
Yes, because the Fock-Planck equation that describes the thermic fluctuations of a black hole. So we consider the black hole as a thermodynamic system, so there is a thermic fluctuations. So to describe this thermic fluctuations, we use Fock-Planck equations to study the transition between black hole states.
and when you have
Okay, thank you for your presentation. I have a question about the dimension of this black hole. You chose the ADS black hole, and we know that the universe follows the geometry of ds, space-time. And why you choose ADS black hole, and what is the dimension of this black hole? What? 4 dimensional. Okay. And Born and why you chose this metric? And we know that the metric of black hole we have Keir and Kerr-Newman and Rn, and the observatory black hole and astrophysics we use eventually Rn or Kerr-Newman. Can you give us more comments about this metric of Born and thank you.
Okay, so I think I get the question. It's why we have chosen this simplest case because I think that which is very interesting is to look for physics behind the simplest systems, not behind the complicated one. Okay, so yes, we can use, for example, Kerr-Newman black holes, and we can choose a very complicated metric. So it's not very interesting because it will be too difficult just to understand what happens behind. And when we use a very simple black hole or a very simple model, not only in black holes or in cosmology, generally in terms of physics, we look for the simplest model, okay, to modelize our not we don't look for complexities. Okay, so this is it. 4 dimensions. Why 4 dimensions? Yes, 4 dimensions. If we want to see the problem in the ACHEP correspondence, that corresponds to the 3 dimensions of the boundary. It's mean 2 plus 1. It's a very interesting case because I didn't talk about the topology because I haven't time to do this. But I invite you to read this article, particularly one, because we can prove that there is a topological translation in Born and Fell in 4 dimensions. That's mean in 3 dimensions on the boundary. And we see that we have, in dance and matter physics, for example, we have some topological translations like Hall effect and so on in 2 dimensions, meaning 2 plus 1, which is very interesting.
and I suggest we use a coffee break for more details about it.